Hey everyone, my name is Peter Hase, and in this talk I'll be describing our work on learning from natural language explanations. This work was done with my advisor, Mohit Bansal at UNC Chapel Hill. We have two main goals in this paper. First, we want to formally characterize approaches to learning from natural language explanations. By this we mean giving formal graphical models for existing approaches that help us tell how they relate to one another. Second, we propose a synthetic task for studying how models learn from natural language explanations. We believe this task will be useful for future work to verify that their models can learn from explanations in the first place and to further investigate how their models achieve this. To begin with, let's establish some terminology. By explanation, we refer to an answer to a why question following Miller. Here's a hypothetical example. For a task that is giving travel times by car, we have an input. How many hours does it take to travel from Addis Ababa to Dessie? These are two cities in Ethiopia. The answer is about 8 hours. An explanation breaks down the reasoning behind the answer. If the two cities are a certain distance and you can average a certain speed, then that gives an estimate of the travel time. We don't try to be more formal than this, and we refer interested readers to Miller for further discussion. Now for some motivation. What is explanation data good for? We see a lot of past work trying to use this data to improve model task performance. The intuition behind these approaches is that while standard supervised learning makes use of XY data, explanations of individual data points should be able to provide valuable additional information for solving a task. One can draw analogies to how humans teach each other to do tasks, often involving explanations for individual demonstrations, rather than just the demonstrations alone. Some approaches here have been successful. We single out 4 examples here. But many have not been able to improve task performance with natural language supervision. One of our past works, among others, falls into this category. So, what goes wrong when we can't learn from explanations? There are often many possible reasons a deep learning method doesn't succeed, and this is no exception. Perhaps we haven't explored the spacing methods enough for these tasks. Or maybe the pre-trained language models people are using already know the information in the explanations and don't even need them. Or language models may not be able to get any more useful information out of the explanations than they already get from the demonstrations, that is, the XY data. To help stimulate research in this area and figure out when models can learn from explanations, we want to characterize existing methods in a formal framework, and we propose a synthetic task for studying how models learn from explanations. We cover our formal framework first. We find that, to date, explanations have been used in modeling as targets, model inputs, and model priors. There's quite some diversity in existing methods as a result. We give the graphical models for methods that we've seen so far. Some individual edges may be added or removed depending on the paper. We denote explanations as E, inputs as X, and targets as Y. Capitalization indicates that a variable is a set. First, we describe a simple family of methods treating explanations as targets, known as multitask models. We've involved generative models for explanations. Across several papers, we do not see any improvements in task accuracy from using natural language explanations as targets. In fact, it might even be concerning that models can learn to generate fluent explanations for their decisions without this process actually influencing their underlying decision-making as measured by task accuracy. Second, many approaches treat explanations as model inputs. The key here is to devise a method that does not require explanations at test time. 2 examples here include the global set and retrieval methods, which see performance improvements with BERT models. In global set, a single representation of a set of explanations is used to A-label prediction for every data point. In retrieval, explanations for training points are retrieved given a test data point in order to A-label prediction. We characterize a few papers as using per data point inputs, meaning they do use explanations at test time. These approaches only really make sense if you're willing to collect explanations at test time too, which could be reasonable in a human-in-the-loop setting, for example. Some more papers treat explanations as structured variables or focus on in-context learning. The structured variable approaches generate explanations before conditioning on them to produce predictions. Similar to multitask models, these approaches are generative, but have not been clearly demonstrated to learn from explanation data. An exciting recent direction of work focuses on in-context learning in a few-shot setting, also known as prompting. Lampinen et al. See improvements from using explanations after the labels for each example in a k-shot prompt, which is represented in the graphical model shown here. Tau represents a latent task, and we do not show the dependencies across data points that are implied by using an autoregressive language model. Note that they only start to see improvements at the 180 billion parameter scale. Interestingly, other recent work from Wei et al. Showed that by putting explanations before the labels in the prompts, models with at least 50 billion parameters also benefit from in-context explanations. In graphical model terms, that corresponds to reversing the direction between E and Y. Wei et al. Actually take care to distinguish their chain of thought reasons from explanations. But the step-by-step reasoning chains they consider look quite similar to our own motivating example in this paper that explains why it takes 8 hours to travel between two cities. Lastly, we have methods that use explanations as priors. One semi-supervised method, babble-labble, uses explanations to get rules for labeling unlabeled data. In effect, this approach brings the final learned model in line with a model that is partially specified by the rules that are derived from the explanations. So here, explanations act as a prior on the model. Next, a large number of works place priors on model weights or feature representations using explanation data. However, very few of these works actually use free-form natural language explanations. A couple papers directly generate model parameters from textual data by means of hypernetworks. For these methods, explanations define a model prior, not in the sense that the prior is not conditioned on data, since the prior is conditioned on explanations, but in the sense that the final learned model is meaningfully constrained by the explanation data. Now that we've outlined the space of approaches, we can ask, which directions are the most promising? So far, we see that explanations work best not as targets or as priors, but as model inputs. The global set and retrieval models have worked well at BERT scales, while at model scales of 50 billion parameters or more, in-context learning is beginning to work with explanations. Overall, we recommend further exploring each family of approaches in case better methods have yet to be uncovered or yet to be unlocked by increasing model scale, available data, or other factors. Now we want to propose a synthetic task for studying explanation data. We think this will help us better understand the usefulness of explanation data. We introduce a task with explanations for each data point. We'll explain what the data looks like momentarily, but we want to say up front that it'll be good to debate how our synthetic explanations share properties with real explanations you might collect from people. One advantage of this approach is that we can carefully specify the manner in which explanations are helpful for the task. We're following a recent line of work that has made good use of synthetic data for studying model behavior, including for pre-trained language models. After introducing data, we show that our models can solve our task by using explanations, while they struggle to perform the task without explanations. This leads us to suggest that models that can learn from explanation data should solve our task. That is, our task should serve as a useful development tool for researchers working on new methods for learning from explanation data. Further, we also show how to make our task harder to solve, even with explanations, so that performance on the task will not quickly saturate. The task itself is to count whether there are more A's than B's in an input sequence for two numbers A and B, meaning it is a binary classification task. The tuple, AB, is called the label reason, since the reason a label would be 1 is if there are more A's than B's, and the reason it would be 0 is if there are more B's than A's. For a given input sequence, the integers A and B can be inferred from the first two integers in the sequence, which are called the index and the indicator. Let's look at an example to see what the explanations look like. We have an example input here, 20 numbers. The explanation contains the index, that input, its first element, plus 4 other numbers. For every data point, the label reason is given by either the first two or the last two numbers out of these 4. Whether it's the first two or the last two is determined by the indicator in the input sequence. If the indicator is 1, then for this data point, the label reason is 80 and 40. And we need to count whether there are more 80s than 40s in the input. Since there are more 80s than 40s, the label is 1 here. But if the indicator had been 2, then we would count whether there were more 17s than 27s. And if the index had been a different number, then we would be considering a different explanation entirely. With different numbers, we might need to count. Different data points in our task vary in terms of their explanations and the random distractor numbers in the input that will never need to be counted. To get data splits for training and testing models, we first get 5,000 training points with 10 points per unique index. That means that each unique explanation is repeated 10 times in the data. Next, we get 10,000 dev points, which do not appear in the training data, but which do use label reasons that are present during training. And finally, we get 50,000 test points in the same data. All of these numbers are easily adjustable. We generate enough training points for reasonable and stable model performance, and we use a large test set in order to reduce noise in evaluation. Next, we argue that there are a few key similarities between our data and real explanation data. First, the index is an easily computable feature connecting the input to its explanation. Second, the indicator is a feature in the input, which tells you what information from the explanation is relevant for the input's label. The reason we have this feature is to require models to combine information from the input and an explanation in order to arrive at the right label. Lastly, and most importantly, our explanations give the reason why data X gets label Y. In our example, the input gets label 1 because you need to count 80s and 40s, and there are more 80s than 40s. Now we want to do some proof of concept experiments showing that the task is solvable with explanations, but difficult without them. We could use a variety of models for this, but we choose to use a retrieval-based model based on Zhao et al. This means that we will learn to retrieve explanations from the training data to help with prediction and test time. We use Roberta-based models as our classifier and retriever, and our baseline without explanations is just a Roberta-based model. First, we ask if explanations are helpful for solving the task, using two distinct but similar kinds of retrieval models. We see that all of our retrieval models perform much better than a baseline without explanation data. With 5,000 training points, the baseline gets around 62% accuracy, while a learned retrieval model gets upwards of 98%. The retrieval models even do better than a baseline with 10 times the training data, meaning 50,000 training points. So we conclude that explanations are very helpful for solving the task. Next, we want to better understand why the task is hard without explanations. To do so, we vary how many label reasons there are in the task, which is the number of different integer pairs that might need to be counted. This means varying how many unique explanations there are in the data. So that's what we'll see on our x-axis in a moment. We hypothesize that when there are many label reasons, the baseline will struggle. This is because it will be hard to infer the label reason from the index and indicator values in input. Indeed, we see that when the number of label reasons in the data is low, the baseline is able to perform on par with a model which is always giving the explanation alongside the input. But as the number of label reasons increases, the baseline is no longer able to infer the label reason from the input, and the only model that continues to solve the task is one that always has access to each input's explanation. It's worth emphasizing that any baseline should be able to get at least 50% performance here. As long as there is a relationship between inputs and explanations, and between explanations and labels, the baseline will be able to capture at least some of those relationships to predict the label from the input alone. From these initial experiments with our data, we conclude that our task is hard for BERT-style models when the number of label reasons in the data set is sufficiently high, and that models can solve the task when given access to training explanations. To recap, in this paper, we wanted to formally characterize approaches to learning from natural language explanations, which we do by discussing graphical models for existing approaches. And we wanted to provide a good testing ground for methods for learning from explanations, which we do by presenting a synthetic task, which is solvable with explanations, but very difficult without them. We investigate a few more research questions and an extended technical report on the topic, including how this task can be made harder for models even when explanations are available, and how explanations can help models learn to use causal features rather than spurious features. Thank you for listening today, and please feel free to see our code base provided here, or contact me directly with any questions.